Epsilon Aurigae is a bright star in the constellation Auriga, the charioteer. It's sometimes referred to as Almas, the billy goat. It's bright enough to be seen with the unaided eye in most light-polluted cities. It's also huge, 2,800 times the size of the Sun. If it were in our solar system, it would swallow Mercury, Venus, Earth, Mars, Jupiter, and Saturn. In 2009, it will undergo a rare event that only happens every 27 years, or about as often as a man will stop to ask directions. During that event, it will lose about half of its brightness. Exactly why this happens has perplexed astronomers for almost 200 years. Despite all of their fancy equipment and computer models, Mother Nature continues to stump us on this one. What we do know is that Epsilon Aurigae likely consists of some stars closely rotating around each other, like celebrities at a posh Hollywood cafe. Exactly how many stars, we don't know. They rotate within a single flat plane just like our solar system. From Earth, we see the plane as edge-on. Sometimes one star blocks the light from the other, causing the entire system to drop in total brightness. Astronomers call these eclipsing binary stars. Systems like this, the more massive stars called the primary, and the less massive stars called the secondary. Think of Laurel and Hardy. The primary is Hardy and the secondary is Laurel. The problems with Epsilon Aurigae lie mostly with the secondary star. During the eclipse, it seems to disappear. One of the most powerful tools in astronomy is the spectrograph. It allows astronomers to break light into its component wavelengths. The primary star and the secondary star should have different types of spectra because they're different types of stars. So when the secondary eclipses the primary, we should see the primary spectra diminish and the secondary spectra increase in relative strength. Imagine shining red and blue light bulbs next to a wall. The light on the wall would look purple. Now move the red light in front of the blue one. Much of the blue light would be blocked by the red light bulb, but some of it would still pass by. As a result, the light on the wall would become purplish red since it now has more red than blue light. But with Epsilon Aurigae, there's no spectral evidence of the secondary. That is, astronomers detect no new spectra during the eclipse. They only see the primary spectra. It's as if the secondary wasn't there. This, plus other observational evidence, has led astronomers to theorize that the secondary is not actually a simple star, but something much more complex. It may be one or even two stars surrounded by a perpetual dust cloud, like Pigpen. So some scientists think we have a dust cloud that has one or more stars within it, all together orbiting the huge primary star. The eclipse lasts about a year and a half, and about midway through the eclipse, the star quickly and briefly regains a portion of its brightness. This may be evidence of a hole in the dust cloud, allowing extra light through it. Now here is the most bizarre part. In addition to the eclipse, the star seems to pulsate in brightness. That is, every few months it seems to gain and lose a tiny bit of light. But over the last few decades, this pulsation cycle has dropped from about 3 months to about 2 months. This could be caused by an unknown object, perhaps a planet or protoplanet spiraling into the star. As it spirals in, it moves faster and faster. If it continues at its current pace, then it would impact the star by the middle of the 21st century, or perhaps sooner. If so, it may cause some very exciting interstellar fireworks, making it one of the brightest objects in the sky. Or not. Frankly, astronomers don't really know what would happen in such a scenario. They can only speculate and keep watching. We don't have a solar system-sized laboratory on Earth to test the hypothesis. That's the beauty of astronomy. Our laboratory is the sky itself, and it's open for everyone willing to look up. Epsilon Aurigae is too bright for most large observatories to observe in the visual wavelengths. Even backyard telescopes are overwhelmed by the light of such a bright star. That's where you come in. With the support of the National Science Foundation, astronomers have organized a citizen science project called Citizen Sky. Their goal is to train the public to make visual estimates of the star. Basically, you go outside and compare the brightness of Epsilon Aurigae with the brightness of other stars. Then you submit the estimate to a central database. Such estimates are of medium accuracy, but when thousands of such estimates are combined, astronomers can get very precise and accurate measurements of the star, so they need as much help as they can get. Another goal of the Citizen Sky project is to turn participants into researchers. We want you to participate in the entire scientific process, not just data collection. You can process data, analyze it, and even write a paper about it for a professional astronomical journal, which is going to dedicate a special issue to this star. And if analysis isn't your forte, we have projects for artists, writers, programmers, you name it. The scientific process is very long and wide. There are steps in there for anyone to contribute. And we have mentors who can help you on the way to becoming a scientist. If it sounds interesting, visit citizensky.org. But be warned, this can be addictive. Clear your plate for the next few years. And thank you for having patience to make it through these litebrite diagrams. Here's a professional illustration of the Epsilon Aurigae system by Brian Teamy. Clear skies.